Thank you. And why it matters much more for the region. To look at the state of the power generation in the region, uh, what has happened within 2022 and 23 is all the new demand that has come up has been met by incremental coal and gas generation. One major theme that I would like to drive home here is despite addition of hydro year on year, the generations have been fluctuating, as you can see on the lower chart. This predominantly means that hydro as a technology becomes much more variable and variable with climate risks aggravating drought-like conditions, aggravating more happening of El Nino type situation, right? Uh, so if you try to look at any of the modeling pathways that have been arrived at by various different organizations, you expect roughly a 3 to 5 times addition, multiplication of renewable energy by 2035 for any meaningful decarbonization effort by 2050. Uh, and given we have seen the problems of hydro in the past, a lot of the heavy lifting would be done by solar and wind. Solar actually fits the case pretty well. If you see some of the major demand centers, um, solar overlies the load curve, and it's a perfect match. And I think as a generation technology, solar wants a demand profile something like this, and which is there in parts of the ASEAN region. Again, there's a wide complementarity between solar and wind. And as we might be knowing in this part of the world, probably also in South Asia, solar complements wind pretty well. So during the afternoons, you have high sunshine, but during the evenings, you tend to have wind, right? And that's the daily complementarity, but there's a complementarity on an annual basis also, where seasons like July and August, when you have like a lot of cloud cover, tend to be actually windy seasons. Uh, but again, in places like Laos and Vietnam, you see a lot of wind resources coming during winters, which again supports the complementary cause. And a lot of this logic actually gets feed into the interconnections that are being planned across the region. And of course, if you compare different technologies across the region, one thing comes out clearly that solar is, of course, has become very cheap over the last few years. It's one of the cheapest generation technologies. Also, technologies like a combination of solar and battery have started to challenge coal and gas in various markets, right? So LCOE as a concept might be very fraught because for example, solar might be generating just 25 or 30% of the times. But then again, making it dispatchable, which means adding more battery and having more predictability around generation, is actually a step further in making it similar to the stance that coal has achieved in terms of dispatchability. So it's definitely a progress that we are seeing. So there are three major themes that are actually coming up for the electricity sector across the world and this part of the world as well. And I would try to bring a small case study or research that we conducted for India. Uh, so electrification is a major theme that's coming up, and electrification across two sectors, the industrial sector, the transportation sector. And a lot of these technologies, a lot of the heavy industries can be electrified and as a result decarbonized by two different methods. One is a direct electrification, where you are actually trying to add more electric arc furnaces, add more smelters to your mix. But then there's the other part where you can't do anything and you have to use green hydrogen there, right? And this adds tremendously to the electricity requirement in the system. And as you can see here, that if you, in such a scenario where you have some moderate electrification, you have close to 3 times of electricity growth coming just for industries. Again, data centers is a major theme that would require 24 by 7 renewables, because some of these companies which operate in this space have a mandate for 24 by 7 renewables, right? And some of the countries are already picking up the data center, right? So, given these two themes where having renewables throughout the day becomes more important, a cleaner grid becomes more important, flexibility becomes very important. And by flexibility, I would like to break it down. One is the geographic flexibility, that means having grids interconnected, right? And the other is a temporal flexibility, where you're having small storage weather batteries, large storage, probably 8 to 10 hours, having pumped hydro, and maybe long-term storage, which in principle the technologies aren't commercial yet at this point of time. So talking a bit about storage, we try to model industry trying to consume 100% RE. So on the x-axis, you have the RE consumption increasing. To meet 50% of its demand using RE, you can do it with a mix of wind and solar, right? And you oversize it fairly. But as it increases, beyond 65%, you need to add batteries. There's no way out. And that's the role of storage that comes in. And what happens at 100% is a very interesting thing. Your share of wind actually comes down. I'm sorry, Elvin. Your share of wind actually comes down because you don't want a lot of uncertainty in the system. You want much more predictability. That's number one. And in order to achieve the last few percent, your batteries needs to scale up because you're trying to deal with a lot of uncertainty. So that's the nature of battery storage and a 24 by 7 grid. And in order to take consider the last few percent, you need to have some flexible generation, which might be gas peaker plants or very cheap storage, if that might come in some days. And again, the the second part is interconnections. We have done some studies around there. There are two main regions, and I think this has been emphasized a lot in yesterday's all the sessions. So in the greater Mekong region, you have these interconnections between Laos to Vietnam, Laos to Thailand, which actually give you one of the better returns in the short term. Then you also have a very big proposition coming if you are linking Indonesia with Philippines and having the trade. So these two interconnections and these two short-term regional networks actually are important for any meaningful decarbonization and economic efficiency. Uh, One thing that is very important here is a country like Malaysia needs to play the role of a exchange, right? And that's a big ambition that one should have of having operating a power exchange. For example, centers like Hong Kong and Singapore have become really big just by transacting capital, right? So if in the vision of the world and if you're trying to set up a power exchange for the entire region, that can be a reason for prosperity as well, right? And the zero shows basically it's a egg, it refers to egg, so it's a chicken and egg problem. You need to have enough generating capacities in order to get those interconnections built. Yeah, just summing up, this has been again told again and again, so I won't go there much. Having grid codes harmonized across regions become important. Understanding these compensation mechanisms, whether it's 50-50, 10-90, these all things become important. You need to gradually move towards a market-based mechanism where you are able to buy and sell power on a real-time basis to match any shortfall as you have more and more renewable. So these are some of the structural, regulatory, and technological changes that you need to have. Thank you. If you are more interested for the Southeast Asia work, these are my colleagues who are working on it. I presented some of the research on behalf of them, as well as my research as well. Thank you.
Thank you. So next we have Phil from Mark McDonald. He will provide us with lessons learned from a relatively new technology, floating PV, and how to scale this in deployment in ASEAN. So I don't think I need to introduce MOCMAC. They are one of the biggest energy management, engineering management consultancy here in the world, and very much involved in numerous major infrastructure and civil works. And Phil has a focus on utility scale, solar and wind. supporting more than 80 gigawatts of projects in Asia. So Phil, welcome on stage, and please also give him a warm welcome. Thank you.
Yeah, so good morning, everyone. Here today to talk about marine floating solar. So slightly different take. I've got another session later on issues relevant to the ASEAN grid, which is a bit nearer term. This is a bit potentially longer term as a widespread solution for the ASEAN region. Briefly on Mott MacDonald's, as Elvin mentioned, we're very active across multiple infrastructure sectors, including in the solar, wind, hydropower, renewable energy space. So for those of you not familiar with floating solar, just to define what the key technology is, we have on the left here, this is going to work for me. Okay, on the left here we have the traditional modular pontoons, which they're HDPE, they're type of plastic float, they're hollow. You can see there that the individual PV modules are mounted on floats. There's also floats that comprise walkways between them, and then there's floats around the perimeter for ballast or flotation. And you can see on the bottom left a little bit of a kind of close-up picture of what that looks like. If you've ever taken a boat to a small island, you may have ended up being taken out of the boat onto one of these that comprises a sort of temporary pier. So it's very similar technology. And this is well proven. There's schemes of up to sort of 500 megawatt operating around the world. It's considered bankable, at least for relatively calm freshwater conditions, right? Whereas on the right, we start looking at technologies that are more adapted to more extreme environments. So you might have something with essentially a metal or other rigid FRP, for example, mounting structure, and the floats underlie that structure. So it has more rigidity. So if you've got more wind or more waves, it's going to be more resistant to fatigue. And then you've got solutions that are not based on pontoons at all, like this. Oops, sorry. It's a little bit difficult about the other pointer, but anyway. The circle that you can see there is an ocean sun solution based on fish farms. It's a similar structure that's used in open water fish farms, and you have a membrane with the PV modules mounted on top. And at the bottom right there, another solution that's under trial in the North Sea. This is a moored and anchored solution. Those piles don't extend to the seabeds. It flexes in the middle, essentially. So there's a range of different solutions out there, but what's currently considered widespread and bankable is what you see on the left. And here's a range of the projects that are already installed, mostly in the kilowatt scale. And different solutions, different places, including some in Indonesia. Swimsaw has a system installed in Indonesia right now. And here's some bigger ones that are also operating on seawater. There's a 5 megawatt system in the Straits of Johor from Sunseap, and a 440 megawatt complex that's now operating in Taiwan in a sheltered bay. This was built out in phases, and the different phases have different technology. We were involved in the first 2 zones. And we'll talk a little bit more about the differences between these technologies. You can see, I'm just going to resort to using my finger. This area there is a floating substation for the Sunseap project. It would then use a subsea cable to go back to shore. Whereas the Changhua project to the bottom, if I move on, you can see it's actually got this pier that runs through the middle of the project. So they actually built this to host the MV system, and all of the DC cables come to the pier where it's changed to AC there. So there's no floating electronics, essentially. It's all on the pier. Another quite interesting solution that's used for the later phases of this Changhua complex is, instead of using traditional anchoring would be blocks which might be buried, or it might be a simple metal anchor. It's more similar to what you see on a ship. This is actually using what we'd call guide piles You would see these on floating docks. So again, you might walk down a passenger gangway and you'd see that the gangway is flexible to go up and down with the tide, and it would have guide piles on either side. Similar concept. And so you have they call it a pillar and a pillar ring, and the ring would go up and down the pillar, and you would moor to that pillar, which means the mooring lines can be much shorter, they can be much more flexible to different tidal conditions. They don't have to change angle, which shifts the position of the floats as they go up and down. So some interesting innovations in this space, using pretty proven maritime technology. So what are the challenges we're dealing with? This is any kind of floating solar, whether it's freshwater or marine. We have to deal with wind load, and we have to deal with the waves. The bigger the water body, the more waves we get because of fetch. Variation in water level, that could be on a hydropower reservoir where it goes up and down by many tens of meters, or it could be a tidal scheme, so you have to worry about the tidal movement. Anchoring and mooring design, this is the core of a floating system, and this will determine the economics of it. You know, depending on how complex the anchoring and mooring is, it drives the cost, which drives the viability. Does it make sense to use floating? Should you be using fixed? Can you install it at all and be competitive with structures on land? And then humidity and corrosivity. Any floating scheme will be more humid than a land-based scheme, so you might want to pay more attention to the specification of your materials there, including your module bill of materials. If you're over the sea, clearly you have to specify all your materials for that saline corrosion. Another significant consideration is biofouling. You get accumulation of biomass on the underside of the floats. Birds like to hang out around these installations. A lot of bird droppings, need a good cleaning scheme, etc. So several of these projects have gone wrong, and you'll have seen this in the press. There's been a number of projects that have failed during typhoons, especially up in Taiwan and Japan, including the largest project that was installed in Japan did fail during a typhoon, and we're lucky to have a public root cause analysis of that was sponsored by the ministry. So most root cause analysis reports we see don't see the light of day. So this one we're allowed to talk about. There's been some good lessons taken from the industry, but I think the point I would make here is that there are no fixed design codes for this kind of installation yet. They're still in the works. Even the ones that are in the works are going to be more for freshwater, not necessarily for marine installation. You ask different float suppliers for designs, you'll get different answers. So this is still a very sensitive area in terms of applying good design practice. Another point that we've actually seen surprisingly commonly is that there's been inadequate temporary mooring during construction. So you've got a period of vulnerability where you have not installed the anchors and mooring lines and you're still installing the structure. We've seen a number of big projects not implement good weather forecasting or good sort of emergency response plans or good temporary mooring. And you can see in the top left there, you end up with damage to the floats before they're fully installed when the high winds come in. So just some examples of the kind of issues that you need to look out for. So where's the potential? If we're talking marine floating solar, where could that apply? I think this is a nice example in that it's quite near term. So this was a saltwater bay in Batam. So it's the Durian Kang Reservoir. This is going to be developed into a 1 gigawatt scale floating solar project for export of power to Singapore by a subsea cable. You can see in the bottom right there, this reservoir has actually been closed off to the sea now, so it's not strictly connected to the sea, but it's a very similar concept of what you could do in other parts of the region, in archipelago geographies like Indonesia and the Philippines, where you have these more sheltered contexts. They would be ideal for large-scale rollout of floating solar that doesn't compete with other applications. You know, obviously you need to be careful about other stakeholders, including fisheries, but you're not directly competing for agricultural land, for example. Yeah. And I mean, we definitely would see that the availability of suitable land in somewhere like Indonesia with very steep geography will start to become limited as you go out into the late 2030s into 2040s. it's an archipelago geography. Is it cost effective to run subsea cables with the right capacity between all islands to be able to connect up where the potential sites are with where the demand is? Or could you use more of this kind of solution? So that's the prize, I think. Okay, and to make that prize realizable, I think there's a number of actions that the energy community will want to take, because this technology is still emerging. It's unlikely that this will happen just through private sector initiative alone. Some sites, yes, but as a broad scale solution, probably not. And so there's work that can be done in a few different areas. I think we're probably up on time, so I'll leave this for discussion if people are interested. Thank you.
All right, now this leads us very nicely to the next speaker. We have Professor Penny from Sydney University Law School. She's an expert legal consultant for UN. Her research work focuses on regulatory frameworks for renewable energy deployment and circular economy. She has often been cited by international organizations such as IRENA and IEA and IEA. And today she will zoom in on PV recycling and also policy and legal responsibility behind it. So let's welcome Penny, Dr. Penny.
I often get asked why there is a lawyer in the room, but we've heard a lot about the need for regulatory frameworks and the role of regulatory frameworks in creating markets. And so what I'm talking to you about today is some research that's being funded by the Australian Research Council. It's a 4-year project. I would very much like any help from people in the room. It's quite a gnarly problem. And I know that in a room full of energy nerds, somebody will be able to help me with this challenge. So the problem that we've got, and you would have neatly seen this in Phil's previous slides, that there are over 50,000 different PV solar products on the global solar market. So we're talking about different chemistries, different designs, different sizes, and that actually poses a really significant challenge for us. In addition to that, we've got these recent solar innovations, so things like perovskite solar panels. As you know, if you've done any work with solar recently, TopCon technology is now kind of flavour of the month, but we've got older panels that have lead and cadmium in them. We've now got those type generation 3 panels coming onto the market. There's increasing interest in printable solar cells. And I say that as somebody from a country with the highest penetration of rooftop solar in the world. So we now have 1 in 3 homes in Australia have got rooftop solar. And in Australia, we're looking at 90 million individual solar panels currently on residential rooftops. So it creates a real challenge then when you think about, well, what happens to those panels at end of life? And what I would suggest to you is that when we were designing solar panels, we were traditionally very focused on reducing the cost and driving up performance. And we've done that incredibly successfully. As you would have seen, this is research cell efficiencies, and particularly with the perovskite panels coming onto the market today, we have absolutely succeeded in really focusing on driving up that performance and that efficiency, and while simultaneously driving down the cost curve. But what we haven't done is nobody's really been thinking about recyclability, reuse, repair at end of life. That wasn't a central driver when we were designing solar panels. And the reason why I wanted to talk to you today is, I'm going to put it to you, it's not a driver when we design any new renewable technology. What we are essentially doing is designing clean, green technologies without thinking about the end of life. And I would put it to you that we can no longer do that. In an environment where we're increasingly worried about critical minerals, we're increasingly worried about supply chain security, it is no longer acceptable to design products, but these all come with trade-offs. For me to create a panel that is low cost and high performance, I lose out on recyclability. And these are business decisions that will need to be made. So currently most PV solar products go to landfill at the end of life rather than being reused, repaired or recycled. And IRENA estimates that there will be 78 million tonnes of solar waste in landfill globally by 2050 if we don't take action on this. So this is increasingly getting more awareness. As we talk about the circular economy, we really are starting to focus on what does that mean? And in some nations, that actually has meant that they have been shipping their used solar panels to Africa. But I would argue that, again, that is no longer an acceptable solution. So I've got these 7 fundamental challenges. So what I'm trying to do in my research is I'm trying to design an economically feasible market that works. Because one of the big challenges when you talk about recycling is that depending on how you recycle, solar panels are actually incredibly hard to recycle. It's 13 layers, and the valuable materials, other than the aluminium backing sheet, are very thinly smeared across the solar panel. So if I'm not shredding it, because if I shred it, I get low-grade polysilicon back, but if I'm actually manually stripping it out, or if I'm using chemical processing, that materially affects the raw materials I get back. So I've got this challenge about the economics. The economics at the moment for recycling, unless you're in somewhere like the EU, simply don't stack up. It is not economic to recycle. It is more economic to make a reuse repair case because people are willing to pay for that, but it's still economically challenging. So the 7 fundamental challenges I've got at the moment when I'm thinking about this market design and how to regulate for it are, we've got fluctuating volumes of solar being recycled. People are increasingly pulling solar panels off early because they're upsizing their systems, so we're getting early retirement. There is a lack of available data in many markets. People simply don't know who has put on solar panels, what the size of the solar panels are, what their chemistry is. It's challenging. There is this real need for economies of scale. It only becomes economically viable to set up a recycling facility once you get sufficient scale. We've got this huge diversity of products within the market, so it's not as simple as say, well, one solar panel is identical to another. We've got a lack of available and affordable testing for the second-hand market, which means that you can't necessarily easily give a warranty. A lack of recycling facilities, and then there's the cost issue. So there have been a number of regulatory solutions around the world. The Asia Pacific is a challenging market for us because if you think about it, unlike in Europe, we all have a lot of island economies. There's always going to be a travel issue. How are we going to transport the solar panels? How do you actually get sufficient scale? How do you get around the international conventions that ban the export of waste? How do we do that? So in Europe, they've got the European Union directive, which both bans the landfilling, mandates recycling, and also mandates increasingly recycled content going into new panels. And well, they're doing it at the moment with batteries. The plan is to do it with panels. In Victoria, they've banned panels from landfill, but that led to stockpiling, and that has created issues. California actually changed the classification of panels from being hazardous waste to non-hazardous or universal waste because they realised that the classification as hazardous waste was causing cost issues. And a solar panel is actually fairly safe when you're transporting it. It's not like a lithium-ion battery. You're not worried about a battery fire. So that made a lot of sense. And then obviously there have also been developments in South Korea. I've got here, there are a range of different solutions that you could propose. They all have advantages and disadvantages. Very happy to discuss this in the panel discussion, but if anyone has got any ideas or solutions or brainwaves, I would absolutely love to talk to you more about this because this is a really challenging issue for us in the Asia Pacific and there isn't an easy solution. And I wish there was. So my plea to you today is when you are designing new products, think about the end of life in the design phase, because increasingly you are no longer going to be able to get away with just focusing on cost and performance. People and consumers are going to expect that those technologies can be repaired, that there may be a second-hand market, not for wind turbines admittedly, but for things like smaller scale distributed energy resources. And so we're going to have to come up with solutions for that. So I've suggested here that we need to really fundamentally reorientate our regulatory framework to look at the whole life cycle of those technologies and also critical mineral recovery. I've got here some questions for legislative design. Again, happy to take those in the panel. But these are some key questions that are affecting how I'm thinking about regulating this space. Suffice it to say, you are not going to get a market for recycling unless it is mandated. So there is always going to need to be regulation in place, because voluntary approaches we know in this space don't work. The good players are already doing it. The problematic players aren't. And also PV solar manufacturers tend to turn over fairly rapidly, some of them, and they may not be around by the time you get to end of life. So thank you very much. Looking forward to the panel discussion. Thank you.
Okay, last presentation of the day. We have Samrat from Deloitte. Initially, we have another panelist, but she couldn't make it due to visa issue. So Samrat took up the challenge yesterday, late afternoon, and he will be presenting to us on the major challenges on renewable energy asset management and how he and his team is leveraging the power of AI and GIS to enable smart prediction, decision-making, automation, and recovery in the face of climate-induced disruption. Very long. So Samrat is a chartered accountant by profession, 18 years of experience in power sector, has implemented large-scale ERP system and asset management solution. Again, I don't think I need to introduce Deloitte. So Samrat, welcome to the stage.
Thanks, Alvin. After 20 years of working as a consultant with ADB, this is the first time I'm coming to this forum, so I'm honored, and it's a privilege for me to present some experience and insights on this topic, advancement in renewable technology. So over the past few days, we have spoken about clean energy, green tech, on the policy, regulatory, commercial aspects of it. But one critical aspect which we'll try to discuss today is the operation and maintenance of the assets which you create. And it's a very crucial portion, because you, as an investor, ADB or any funding agency, do create large scale assets, renewable assets, but who take care on the operation maintenance? So that's the area we are trying to discuss on my presentation. And with power of new technology, AI agent, how can we gather all the data together to make a meaningful impact on making a climate resilient infrastructure planning. So if you go to any large scale utility, we are implementing and installing any type of renewable technology, be it ground mounted or rooftop solars or BESS or hydros, small hydros, DREs. These are typical challenges which you will face. Large utilities, dispersed location, and I come from India, in South Asia region, there's a shortage of technical manpower. So either technical or non-technical to cover all the assets throughout a dispersed location. Go to any province in India, it's like a country in any European space. And typically they rely on third-party vendors. And when you rely on third-party vendors, it is pertinent for the utility management to also monitor their work. And typically you fall out of various contracts. Also, these are legacy utilities. You hardly have implemented cutting edge enterprise level asset management solutions. So you also have lack of data. And when you put a case for new age solutions, there would be delays in adoption of technology in the utilities. So even if you implement, there are a lot of case studies, a lot of money spent on GIS or large scale CRP or say solutions like IV and Maximo. Once implemented, 2 years AMC, after that when money is dried up, nobody is there to take care of it. So and then again you are relying on vendors to get support. The other problem when you have SAP, Oracle, IBM, ERP, you also have to integrate the geospatial data because without data, it does not make any sense to go for an AI. And now we are talking about AI agents. So data has to be there in a proper format. So realizing these issues of Indian utilities, South Asian utilities, we at Deloitte have tried to create a very simple, low-cost solution compared to any COTS product, which costs you around 20-30 million dollars for a typical utility in India. So what we have tried to do is a simple mobile application. For the first time adapter, you have a simple login page, uh, and you go to the field, collect all those asset datas. And when I say asset datas, history of the asset datas for first time adapter, uh, who is the vendor, when it was installed, what is the capacity, what is the condition. So you're using image analytics and thermal imagery to understand the condition of the assets, and break down on the history. We get into the maintenance historical data so that a prediction can be done on the maintenance. Once this data is collected, we send it to a central server, create a portal for MIS dashboard for the management. You also build a map layer on it so that you click on a location, get all the data from a headquarter. So, and once you have all the data, map layers are there, that's where we are trying to build a geospatial AI solution over it. So that if you have an OT device, you can do a real-time monitoring. If OT is expensive, then you have a large field team to give you a regular data on the maintenance. So I'd request to share the video just to have a clarity on the solution you have developed. Can you run the video, please?
Are you fully informed about your assets for effective maintenance? Are all your assets geo-referenced? Do you have a digital repository of your assets? At Deloitte, we understand the challenges electricity utilities face in managing their vast and critical assets. That's why we offer comprehensive solutions tailored to your needs. Our approach begins with a thorough physical verification using cutting-edge, cloud-based tools. Our solutions are designed for efficiency, allowing your teams to verify assets digitally, with features like geospatial mapping, asset componentization, and a streamlined MIS interface. The tool has a built-in approval management system and workflow where verified asset data or changes, e.g., location updates and condition assessments, require managerial or designated authority approval before finalization. His app streamlines asset management for Transcom's grid by allowing users to quickly enter equipment details, mark GPS locations, and capture images for each asset. It centralizes all data, including specifications, locations, and visuals, into one accessible repository, making it easy to track, inspect, and maintain grid assets efficiently. Regulatory and accounting requirements need to be adhered with regard to asset verification and cost determination. This involves handling massive data in terms of multiple locations, time periods, and data formats. Our program management ensures the process stays on track, with regular updates and status reports, identifying potential issues before they become problems. The culmination of our work is a fully compliant fixed asset register, meticulously compiled and ready for integration with your SAP ERP system. We provide ongoing support to ensure your asset data remains up to date and accurate. In Dart, asset details are meticulously organized and securely stored, creating a centralized platform for seamless asset management. Behind the scenes, Dart efficiently integrates each asset's lifecycle information within an intuitive, hierarchical structure that mirrors the organization's real-world layout. This structured approach enables users to access and manage assets at multiple levels, from individual units to entire departments, ensuring that critical data is just a click away. With a focus on transparency and accessibility, DART empowers users to track and manage assets with precision, making asset oversight and optimization a seamless part of daily operations. Deloitte ensures your assets are managed with precision and compliance. Trust Deloitte to provide the expertise and tools you need to safeguard your utility's future. Contact us today to learn more about how we can help you take control of your assets.
So what started as this very simple data collection and asset maintenance solution for the video was for a utility which looks into distribution and transmission part in the central India. And we are now graduating this application to do maintain renewable assets which are spread throughout. So what we're trying to do now as a POC is superimposing climate and weather data and run an AI model into it. So I come from the eastern part of India, a lot of cyclones around our state. So can we predict cyclones and its impact on renewable assets? Can we predict, say, cloud covers over next 3 days, and what is the impact on solar panels and impact on grid? Also, if you have a data from pollution, dust pollution data, what is the impact on our grid? So these are some of the POCs we are trying to integrate on the already mapped asset data. And it also helps in planning. Say, for example, EV infrastructure planning for a city. You already do a geospatial solution to understand where the loads and put a EV infrastructure. Once put it, you collect all the APIs data, monitor the operations of EV. Also during a disaster incident, planning for a disaster, what is the water level on a panel, or what the dust level on a panel. So these are some of the use cases we are trying to do on the already collected asset data. So we talked about risk mapping, predictive maintenance of a renewable assets, and this is not just renewable, any electrical assets can be used by this solution. So risk zoning using GeoAI algorithms. So there are some of the use cases which we thought in case of pre-event, how do you predict, how do you simulate with the data already available, data are cheaply available. Also, in case worst case scenario, you are hit by an event, post-event recovery. So how do you use pictures and image analytics to quickly respond to that situation? And you also do a crew optimization to which area to cater to first. So before I conclude that, we have an asset management solution which can be deployed by 1/10 of a normal COTS product. The open source AI data are available. You are talking about AI agents which run algorithm for you to help you take decisions. So these are cheaply available all over. So overall, if we embed everything together, we are in a position to help create a climate resilient renewable asset management. Thank you.
All right, thank you. And I want to welcome our esteemed panelists again, colleagues on the stage for the rest of the panel. I have some prepared questions for my fellow panelists, so I'll just go to them first. To Tatri, from your presentation, I understand that to scale renewable energy integration into the grid, we need a stable and flexible grid. And recently, there's a case of in the Iberian Peninsula where there's a blackout. I mean, there's a lot of rumors going around. What's the issue? But I understand from you since our chat yesterday that the possible root cause could be because of the sudden drop in renewable energy into the grid, causing the end for the blackout, right? So renewable energy, unlike thermal energy, has initial, and I understand that this drop in frequency caused this problem. Can you maybe share with the audience Your thoughts? What could be the situation? What could we learn from it, and that it doesn't happen in our part of the world? Please.
Thank you for the question. I think it's very pertinent at this point of time. Again, the case of the Iberian blackout has been not yet resolved. There's no official statement out there of the root cause analysis, but one thing that we know for sure is as we have more and more renewables in the system and a system which has more renewables, share of renewables, you have a gradual decline in the inertia that's present within the system, and there are multiple reasons for it. Going forward, I think, and this was something we have been thinking for some time now. So the inverters that we have for traditional solar and wind generation are grid following. So if there are some disturbances in the grid, they essentially follow. So if the grid frequency goes down, they also help it to go down further, right? But then there are solutions coming such as grid forming inverters, where you basically go against the fluctuation of the grid. There are solutions such as synthetic condensers that are coming up, where it doesn't generate, it just absorbs excess power or pushes excess power in the system to balance the system. And last but not the least, I think solutions like predictive analytics and maintenance do play an important role, and it does really make a lot of sense to invest in it. But I think that will only come when you have those regulatory conditions in your markets where your government actually forces you to actually adhere to a particular schedule during the day. So if you are generating more or generating less, then you are actually penalized pretty strongly, and that essentially gets you the incentive to invest in solutions like predictive analytics and better weather monitoring, etc.
Okay, thank you. Phil, Asian have diverse water bodies, right? And reservoirs in Laos, in Malaysia, with natural water bodies. We also have in Indonesia the world biggest floating PV, 195 megawatts of Sirata floating PV. In Philippines, here, we are estimating 3 gigawatts of floating PV potential. In Vietnam, the Dami hydropower is also using floating PV to stabilize the grid during drought. So it seems that the floating PV market is significant. So two-part questions for you. How can ASEAN government and private developers prioritize the sites for maximum impact? And what regulatory framework is needed to incentivize this floating PV projects?
Thanks, Evan. So I think we can break this question down into freshwater and marine. And I think for freshwater, the good news is it doesn't really need much more in terms of the regulatory framework than fixed solar, than land-based solar. There are some subtleties around who's the owner of the water body. There's different stakeholders involved, for example, fisheries on many of these water bodies. But ultimately, the drivers of site selection are going to be very similar to any large-scale solar project. It's going to be, can you get grid? Can you get land? Is there good solar resource, etc. So not much to do beyond kind of making sure that the current regulatory framework does not block floating solar, and making sure that the right consultees or water body authorities are involved in the process. Right? And you've seen that in most countries. And like you say, pretty much every country in ASEAN either has large-scale floating solar on freshwater bodies or has big plans in the works. So it's happening already. So that's good news. I think if we move to the marine floating solar, that gets significantly more complex, and you start getting into the similar kind of issues as we see for offshore wind. And there's a much wider kind of regulatory and planning framework that you'd want to be in place. I think there's also a lot less, the technology gets more complex. Is a site viable or not becomes a much more fraught question. So I think both from a regulatory and a industry capacity perspective, there's work to do. And that would include kind of mapping viable sites, putting out good practice guidance on what is a good site, what is an acceptable tidal range, how close can you be to a shipping channel? What kind of fishing density is acceptable? Some sort of geospatial mapping exercise to actually start illustrating where are the viable sites, and a regulatory roadmap, I think, would go a long way. Yeah, thank you.
Thank you. Next, Dr. Penny. In my world of offshore wind, foundation jackets are recently proposed by the developers as artificial reef. And they claim that these jackets are, instead of being decommissioned, taken out of the water, we keep them in the original site and they can act as a reef. And again, they are trying to prove that that's good for biodiversity in the ocean. We can't really say the same for solar panels. And I note that there's importance of clarifying legal responsibility for end-of-life solar PV. In jurisdiction where extended producer responsibility, EPR, has been implemented, what lessons can we draw on from solar PV regulation, and who is best placed to bear this legal responsibility? And is it the manufacturer, the importer, the government, or who else? Thank you.
Thank you. One of the things about extended producer responsibility, so that's where you put the legal onus for the end of life on normally the product manufacturer. And so if you're in a jurisdiction like I am in Australia, where we import in almost all of our solar panels, largely from China, you're then placing the onus on them to take them back at the end of life or bear the legal responsibility for recycling, reuse, repair. One of the challenges with that is that, as somebody seen in Australia, often the Chinese solar manufacturers actually don't have a lot of assets in Australia. So if something goes wrong in that system, and as lawyers, we're professional worriers, that's my job, so that you don't have to worry, your lawyer does it for you. I worry about, well, what happens if that manufacturer no longer exists? Because we see a lot of turnover within the PV solar market, at which point you would also put a secondary responsibility on the importer. And then you'd also have to have what I call a recycler of last resort, which will probably be the government. And you need to think about who is going to pay for this, at what time are we going to pay for this? Are you paying for this up front when you're buying your solar panels? At which point you're adding additional cost onto the shift to renewables? Are you bearing that cost at the end of life? And then if I sell my panels to a second-hand market, am I just shifting my liability for the recycling costs onto somebody who can probably not afford it? So it's a really fraught system, and it's one that we need to think about very, very carefully. And you always, like with any asset, you need to think about, do you have some way of keeping that person on the hook within the jurisdiction? Do you have any security in case that something goes wrong? So it's a fairly significant problem, but an interesting one.
So, Samrat, I'm glad you're in the house to talk about AI. And of course, for Jumbo Consulting, my company, we are also developing an AI tool for contract management. So if we don't embrace AI, I think we will be soon replaced by AI. So my question to you, can we provide few examples on your AI and GIS solution on the various renewable energy technology, solar, wind, hydro, for example?
So, we had a case where there was a hydro planning required for an investor. There was a dam to be made by the investor, and then you have a lot of water data available, and so when you invest in a hydro, there are a lot of impact assessments which has to be done, but stuck by the data model which is there. So luckily we had a lot of downstream asset data of the utility infrastructure, and we added a geospatial layer, and with modeling, climate modeling, you could simulate if you build a dam, what is the impact on the water level of the reservoir. There was a floating solar plant, what is the impact on the investments downstream, what is the impact on the livelihood or on the nearby channels. So we are embracing those geospatial data along with all the assets data which are collected from the solution. So that was one of the use case. Also, without AI also, if you have not graduated to all those data collected, typically in South Asian utilities, one of the starting case which we had in India, any discom generation companies or transmission can do a solar installation with BESS. There are 3,000 installation in a province, so we are mandated to actually check all the condition of the assets. We use image analytics to understand the condition. So what happens now? It's a good example. We're talking about smart meters. So when you do a smart meter implementation in a province, you actually lose employment of meter readers. So the utility, we give an option that all these smart meter readers can be redeployed and employed in the asset management services with our solution. So that's a fantastic use case which you've done.
Now we open to the floor. I really have questions fast and furious coming in, but is there any burning questions for our panelists now? If you want, you can go to the mic over there. Anybody? If not, I will go. Go ahead.
Hi, I'm Peter DuPont from Asia Clean Energy Partners. I believe I know your dad, Penelope. Yeah, David. Yeah. I have a question for Penny or Penelope, and also to Trataya, and it's sort of related to a question that many of us dealt with about 20 years ago with CFLs, where you had a lot of good quality compact fluorescent lamps and a lot of low quality ones. So the irony was that China made the worst trashy compact fluorescent lamps, but they made the best. And they only when they got regulated and got cheap did the bad ones phase out. And of course that got taken over by LED. So the question I have is, it seems like there's a problem with systemic or life cycle design of products, and you've answered it a couple of different ways at the jurisdictional level, but how can we solve this problem? Because it's going to be, and Samrat, also you talked about smart asset management, right? How can we sort of force or incentivize the design of smarter projects so we don't end up with a lot of incompatible systems, trashy systems? And I know we want a free market, we want to encourage innovation, but maybe thoughts on that if any of you could take that on. Thank you.
I think one of the things that we see in the sector, it doesn't matter whether it's a floating PV system, it doesn't matter whether it's an offshore wind farm. As part of the legal requirements for the big scale systems, they have to provide a decommissioning plan. And as somebody who studied a lot of decommissioning plans from across the region, quite often they say, by the time we get to decommissioning, don't worry, sufficient technology will exist and there'll be this wondrous solution, but we don't currently know what it is. And they normally say that in about 75 pages, which is painful to read. But I think we've actually really got to start thinking about the end of life right from the get-go. And the way to do that is to have a regional solution like the Europeans. The only way we get sufficient scale to actually recycle these technologies is if we take a regional approach, if we actually think about harmonising expectations around product design standards, around kind of environmental impacts. That's the only way you get there. And the sad reality is that's going to mean we have to regulate.
If I can add as well, I previously worked in the oil and gas industry. In Indonesia, there's like hundreds and hundreds of offshore platforms lying in the sea. They are not being removed because they are not part of the decommissioning plan from day one, and the penalty is not big enough for the developers, operators to remove it. And I agree with Penny, Dr. Penny as well, that if this is already, decommissioning plan is already on the onset during auction scheme, so probably this will encourage the developers to already think about decommissioning plan and put it as part of the auction bid. And if this is good, then they get awarded for projects. So that's my take.
So from when you design, at least from the data perspective, what I've seen, suppose at least from our assets has been installed, implemented in a couple of provinces. So we have a lot of real-time data, what is the condition of the assets, vendor-wise, and life-wise. So in a stage of life, how the vendor and asset has performed. So I can tell you in Nepal, from Himalayas to border of India, we have taken photographs and videos of all the electrical assets. So we started with distribution transmission assets, or similar from renewables we are trying to do. And now we're installing in 10 different provinces in India. So as we have a lot of asset and vendor data, we have a history of who performs when and how. So that can be assimilated to do a matrix, which can be used during design phase and procurement phase also.
Elvin, can I just add in there? The other thing we would do is you take a financial surety from day one of the project. So the second that that project starts producing any revenue, you are taking a decommissioning surety and you're holding it in a government account, not in the company accounts, which is controversial, I know, but it's the only way to ensure that you've got the funds at end of life to actually do anything.
Any other ones to speak? If not, I will go straight to the overwhelming questions. First question for Phil and Dr. Penny. Typically, for plastic type of floaters, there's a risk of chemical leaching to the water body. What are the mitigation or prevention for this risk? Is there any product standard like IEC, ISO, or others to prevent it?
Yes, so that is a risk, and the good thing is that these floats have been deployed on drinking water reservoirs, which have the highest standards for the integrity of the float, and that no chemicals will leach out to the water. So there are tests that can be done on the floats. Most credible float suppliers will be having test results that conform with multiple jurisdictions to prove that their float is suitable even for drinking water reservoir use, and therefore is entirely suitable for any other use. Yeah. Clearly, you also have to be careful of the site conditions. Any plastic is vulnerable to UV degradation. You need to be understanding that even over the product life, that it is suitable for those site conditions, in terms of the UV exposure, in terms of the fatigue, because if it's not, then that also increases the risk of any sort of contamination. Yeah.
Okay, next question. What is the incremental investment needed for floating solar compared to ground-mounted solar? I mean, in offshore wind farm, it's very clear that fixed bottom is cheaper than floating wind. We discussed this morning that it's not necessarily the case for floating PV. So maybe you want to have another go?
Yeah, so this is the golden question, right? I would be disappointed if this didn't come up. Generally, floating will be more expensive than ground-mounted, and the anchoring and mooring will be more costly than just a fixed mounting structure with piles into the earth, right? And so if you have suitable land near to demand centers, then you would use that first, right? I think the point is you often don't. And so it's less about the installed cost of the floating solar and the ground-mounted solar, but when you start adding in transmission to actually get from where you're generating to where you need to use the power, that's the more relevant comparison. And that's why many of these projects are going ahead at very large scale, up to gigawatt scale, despite the fact that installed cost for the generation will be slightly higher than ground-mounted. How much higher entirely depends on the site conditions. How shallow is the water body? The deeper, the higher cost. How variable is the water level? The more variable, the higher cost. How big is the wind? How big is the waves? Therefore, how big do your anchors need to be? How do you need to install wave break systems? So it depends on the site conditions. Interestingly, it's not necessarily the case that a marine floating solar system will be more expensive than a freshwater system. Again, just depends on the specific parameters of the site, all of those variables I just talked about. Laguna Lake, if we look 5 kilometers that way, there's 2 gigs of solar with conditional kind of licenses there that are now bidding in the GIAB4 in the Philippines. You get 3-meter waves during storm events there. That is worse than most coastal areas. So you have to consider the site-specific conditions. Luckily, it's also quite shallow and the water level is relatively stable. So there's pros and cons. But often will be more expensive than land-mounted, but maybe not that much more, depending on the site. And you can get much bigger capacity closer to demand centers. Yeah, try finding 2,000 hectares of land closer to Manila than Laguna Bay. Good luck.
There's a follow-up question on is there a cost comparison per megawatt between floating and conventional solar on land? I mean, you mentioned about there's no land, right? Is there a comparison we can make here?
Unfortunately, not any up-to-date public sector comparisons. There are some World Bank reports. They have this series of reports called Where Sun Meets Water, and so you can look up that guidance. We've been peer reviewers for the technical guidance, both the nearshore one and the marine one that's coming out. And that has some numbers, but they're both for the ground mounted and the floating, they're very out of date. This is, you'll see the cost curves coming down for solar, for battery. You can now get EPC at 40 cents for ground mounted on solar. If we look at those older numbers, the floats, huge range, but let's say that they might have been coming at 20% higher generation costs than installed costs than the ground mounted. Unfortunately, every piece of more recent data I have is confidential, so I'm not going to be able to say anything more. Thanks.
Okay, next for Tutatore. Can you explain more why BESS, battery energy storage system, is required for system having more than 66% variable renewable energy?
I'm not very sure where the 65% number comes out, but it's pretty much what we show in some of the work. So if your renewable penetration becomes more than 60 to 65%, you would require more and more batteries. But essentially, batteries, to cut short, do three things. One is they shift your generation across time blocks. So basically taking excess generation from solar hours to non-solar hours, evening peaks. So that's one traditional role of batteries. The second role is when you have more renewables, you have more intermittency, more variability in the system. So you need to have these ancillary service markets where you are actually, or the balancing markets where you are actually taking care of the last minute shortfall. So maybe I realize today that I'm having a huge cloud cover on top of me. And so these are exigencies, these are actually emergencies, and batteries actually play a great role in supporting the ancillary service markets. So that's the second role that batteries play, more or less. I think the third role that is not spoken about enough is battery plays a highly important social role, right? So, for example, it actually differs your capex investments required to build transmission grids, right? So, assume there are 2 points A and B. Let's say A is my generating point and B is my load center. And let's say in the next 2 years, I expect my peak demand to increase by, let's say, 2 gigawatts or 5 gigawatts. So without batteries, I would have had to make transmission lines from A to B, do some network upgrades. But what does battery do is essentially if I put battery, it can solve for that excess peak demand that's coming for the next few years, right? So I can store my excess energy during solar hours, during high wind seasons, and I can use it. So it differs the requirement of lot of interconnections or building large transmission networks. So I think that's a big role that grid scale batteries would play. I think these three are the fundamental big roles.
Yeah. But I understand that the cost of battery is adding 3 to 4 times more in terms of cost to a solar panel farm. So because for typical solar PV module, the cost has reduced significantly over the years. Do you foresee the same for battery reducing price?
I think the trends and the learning rates have been similar. At times, what you hear from market participants that it is much more aggressive because a lot of reports, what they claim in 2023 or maybe middle of 2024, it's totally not valid today when you go out and talk to folks. So there was a time probably within 2024 to 2025 that a battery pack costs reduce from like a 3-digit per kilowatt hour to something which is a 2-digit and maybe lesser than that. So the scale at which it is happening
Tremendous.
is tremendous. Yeah.
Cool.
Can
Right,
I add in an additional point there, which I think sometimes gets missed? Being from Australia, we're really good at, we lost a huge amount of electricity infrastructure and grid infrastructure during our last big bushfires in 2019, 2020. In my state alone, we lost over $1 billion worth of electricity infrastructure, massive amounts. And the one thing that batteries provide, batteries, standalone power systems and batteries in terms of resilience and grid resilience, and also in terms of ensuring, you don't think about this until you're in the middle of a bushfire, emergency communications. People actually need to be told that you've got a bushfire or you've got a cyclone, whatever it is coming. And a battery provides you with that benefit because you don't necessarily, you can island it off. And those benefits are huge. And I think we don't fully appreciate that in the year of climate change, it's going to become a bigger and bigger consideration.
Okay. I don't think I'm able to finish all the questions. We have 14 minutes left, but I'm just going to have one more last question from here before any urgent questions we can just speak and then we can talk about it. So last one from the app. Generally, the renewable energy plant and load dispatch center should be equipped with highly accurate modern forecasting equipment. In that case, how could Deloitte app help for more accurate forecasting?
So, with the application, which is cost effective, which I have showcased, along with climate data, which are freely available over last 100 years, also 50 to 100 years. So with this solution, we are superimposing, and case in a point for a state which we are doing for a renewable master plan, and that state is a cyclone prone. So whether onshore, offshore, where the load centers, where you need ground mounted and what strength of that foundation. So all those data, we're putting it together, and we spoke about which vendors are good for that location. So point here is we're putting all the data in a planning perspective, and you don't have to rely on a costly 20 million, 30 million COTS product. So, nowadays, all technologies are very cheaply available, and these are open source solutions which anybody can use. So we put together, and at Deloitte we have actually implemented from planning to operations, and we showed post-event recovery also you're helping.
Okay. Anyone with questions from the floor? Okay. Very shy, so we go straight back to the app. Because there's a lot of overlapping questions, so I'm just trying to find the right ones. So, back to Phil. What do you think are the most significant challenges in developing marine floating PV, both from engineering and environment, maybe more on environmental, we talked about engineering already, so maybe more on the environmental perspective.
Okay, so yeah, from the environmental perspective, there's a rule of thumb that you don't cover too much of the reservoir. If it actually is, some of these schemes are just industrial ponds, right? There's no actual ecosystem there, right? So that's fine. You can cover the whole thing. But to the extent that they're actually a live ecosystem within the water body, you don't want to cover too much of it, because it changes the change in the insulation actually reaching the water changes the balance of biodiversity in the water body. It's actually not always negative. Sometimes the reduced insulation can reduce algal blooms, but it will change current circulation. So there's a whole set of kind of environmental studies that need to be done for any kind of large water body, especially if you're getting towards covering more than 20% of it. If you're covering much less than 20% of it, the rule of thumb from the environmental sciences is it's not a big deal, right? So, and then there's obviously an interaction with kind of bird life and marine life as well. Some of these schemes that I talked about are actually based on fish farm technologies, and you could actually combine them. There's some talk of combining aquaculture and floating solar. So there's a sort of, in addition to the environmental, there's a kind of social license element. Clearly, to the extent you're building floating solar on a water body that's already used for fishing, you need to allow for navigation lanes, you need to allow for the fact that other users will create debris, you need debris screens. So there's all sorts of kind of interactions with the local community as well. There's some visual impacts you need to consider. Going back to the technical challenges, yeah, we didn't have time in this presentation to get into them in detail. We have a one-day workshop we like running on this, but you know, in addition to the kind of items that I mentioned there, you know, I think it's well worth noting that there's a range of different conditions that you need to consider when you're selecting your technology. And there's like your ultimate loads, there's your fatigue loads, there's the risk of accidental impact from vessels, there's going to be debris that will be borne by the water that will come into your project. You need to design against that. We've had instances of unauthorized access onto the floats causing damage. So there's just a number of items to think through about how this will operate in the real world, in addition to just applying good engineering design practice. Yeah.
Now, Dr. Penny again. Can circular economy or life cycle analysis of newer technology be part of a COP and or UN agenda before it's getting promoted?
I think the reality is absolutely, and these are conversations that we're having with bodies like the UN as part of a whole range of different spheres of influence that they have. The other area that I would push is that if I was financing any large-scale project, I would want to have this in the project design right from the get-go, because the reality is going to be in the next 5 to 10 years, in almost every jurisdiction around the world, they will start thinking about these problems. And what you'll find is that these projects are going to become encumbered with these costs. These costs don't go away. We can pretend they don't exist, but once you hit end of life, they do exist. And we're seeing that with wind, we're seeing that with solar. And the other thing we've learned from oil and gas is that there is a historic tendency to under-financially prepare for decommissioning costs at end of life. And there haven't been sufficient reserves put there because people don't look at decommissioning costs as they increase over the course of a lifespan of a project.
Okay, thank you. This is good. I like this. Tuta Ture, you mentioned that at 100% renewable energy situation, solar is more certain compared to wind. I mean, I also don't understand why the percentage becomes so small.
I thought this slide was really interesting too. Is it actually possible to get it back on screen?
Is it possible to put it back on screen?
So I would add to that question and just say that slide doesn't specify what you're charging the battery with, right? So I guess what you're showing in that slide is what you're dispatching without routing to storage. It's direct dispatch rather than first it goes to storage and then it's dispatched. So I guess that would be good to understand what's modeled there. Yeah.
Yes. Just a disclaimer. My colleague has a session after this where he's going to talk about the 24/7 projects and how do they pan out in India. But since this modeling study was carried out in the context of India, it had some element of uncertainty analysis to it, and given the last 3 years of wind generation in India, we have had massive problems, and my colleague from Deloitte can probably vouch on that, and a lot of wind generators have actually seen profits going down, I mean revenues going down, generation going down tremendously. So I think that's a problem for Indian markets, and a lot of weather modelers and people specializing in long-term climate models say that there's a trend of weakening of monsoons, and this is going to get aggravated and more uncertain. So the project, what it assumes is it assumes a islanded grid sort of thing where you just have an industry, you have solar, wind, and battery. And in such cases, then you want much more stability rather than optimize too much, because at the end that's your only lifesaver. You're not having a fossil fuel source, you are not connected to any other grid. But that, of course, won't happen in the real version of the world, where you are, of course, connected to the grid. At some point you can source something in terms of like shortfall intermittency. And coming back to your question, I think the whole mix then becomes like a combination of solar and storage. Solar oversized to a great extent, batteries partly oversized if you want to go beyond 90%, but then it's predominantly being powered by solar and battery with minimum amount of wind. So that's what we think will be optimal.
Yeah, so I think this is an interesting scheme in India where you can use third-party grid access to effectively have a captive industrial user using a variety of different generation sources spread around the country: solar, wind, pump storage, hydro, battery if needed. And if you model that, you get a certain outcome, which, I mean, the 100% case is always interesting. Once you get above the 95%, those graphs tend to do strange things, right? I don't think we need to worry too much about that right now for most applications, because, you know, we're mostly on the grid, and there will be fossil fuels on the grid for some time. But I think also when you hear people say 24/7 renewables, it really just comes down to definitions. What do they mean by that? At what capacity factor? At what availability rate? Nothing's really 100%, right? Statistically, nothing's really 100%. So you know, I would assume that you would always be able to use wind to at least charge the batteries at night, right? And that would be a useful application. But yeah, you'd have to look at the specific case.
Okay, maybe one last question. I also want to know this as well, because for offshore wind farm, when we go floating further offshore, wind becomes stronger. Is there any additional generation percentage if we go into floating compared to fixed or onshore?
Yeah, so this is a really interesting area. If you're operating over water, you can potentially run the panels cooler. Temperature losses is the main source of loss for a solar system. So in this part of the world, you could lose 10 to 20% of your energy just to the panels running hotter than their ideal condition. So if you're over water, potentially you get the benefit of the convection cooling under the panels. You know, the water is cool, but that just depends on your flow, essentially. Is there an open space between the module and the water that allows for that airflow to happen and that heat transfer to happen? And that's very different by technology. And it's one of those areas where it also depends a lot on how windy the site is. It's one of those areas where unfortunately, all of the research papers that are out there disagree. And if I was doing a very large scale project, I would put in a test bed to measure that if I wanted to capture that upside. Yeah.
But for O&M, it's more difficult to go offshore. It's more difficult to go. I mean, it's not like land you can easily walk and clean and maintain the panels. It's a bit more. So cost of OPEX.
You know, it's
compared to a normal.
It is more complex to access. You know, you see people accessing by jet ski, for example, and you can actually walk along those HDPE walkways in the panels, but clearly access to fresh water for panel cleaning is more constrained. Maintenance activity is more constrained. If it's you know, more stormy weather conditions, you wouldn't attempt to access. Right? You're not going out there when it's raining. Like you know, you can at least access your central inverter if it's raining on a ground-mounted project. But actually, we haven't seen. There are higher OPEX costs, but it's not a primary driver of project economics. Yeah, that's what I'd say.
And to add, Philip, you spoke about swim soul. So in Maldives, the cost of implementation and the evacuation might be a cost interview. So not just O&M, but when you go further, the capital cost might go up, and the cost of evacuation, it might impact the project economics of it. So that can deter your investments.
Yeah, so shorter grid connection is definitely better, right? So being close to shore you'd only go further. Going further out to sea for floating solar is, there has to be a really good reason, right? I mean, it's going to be more challenging environmental conditions and longer grid connections.
Does get you away from having to do with a local government arrangement, though. Like from a planning law perspective, the further out offshore you go, the easier life gets because you're generally only dealing with the national government, and it means that you're probably also not dealing as much with the local community. So it might be faster. Just saying, could have its side benefits.
Give me a big sheltered bay, not subject to local laws any day.
It's an interesting panel discussion. Thank you, everyone, and we are right on dot. If we have any more questions afterwards, feel free to come to any one of us during the coffee break.